Welcome back to Computer Science Theory. This is COMS W3261, Lecture 2. Part 2. And today we're going to talk about non-determinism. Which is a big word for adding a great superpower to our math machines. So we're going to amp it up. So what did we talk about in the last lecture? We introduced these things called deterministic finite automata, or DFAs. And we know, okay, the automata part of this name, that's Greek. That means self-machine or self-doing or something like that. Finite refers to the number of states and the number of symbols in the alphabet. The fact that those two things are finite means we can always write down a DFA in a finite amount of space. They're finite mathematical objects. But we haven't talked much about this first word, deterministic. So if you've taken a philosophy class, you might be familiar with the determinism versus free will debate. That's a concern over whether we actually have any choice in what actions we take, or whether the actions that happen next are completely dependent on the current state of our being. And that's also pretty much what the word means when it comes to automata. Determinism means the next state is completely determined by the current state. Right? That's essentially what we mean when we say our transition function maps from a state and a symbol in our alphabet to another state. We're saying, hand me two things, a state and a symbol, and I'll tell you where you will be in one time step. Totally determined. But it turns out we can break this rule, and breaking this rule will give us some more power in our automata. So that's our idea for this lecture. What if we break determinism? And we're going to break it in a couple of ways. I'm going to introduce new rules for what are called non-deterministic finite automata that'll allow them to work in non-deterministic ways. So, new rules. Rule number one is that now we'll break our rule that every state has to have exactly one outgoing edge for each symbol in the alphabet. If we have multiple options from a state for one symbol, what do? Well, we take both, or we take all of them. Essentially, we split into two branches of computation that run in parallel. So just as an example, suppose I was at this state, and on the input symbol 0, I was faced with, let's say, several options. An edge that goes over here, an edge that goes over here, and an edge that stays in the same place. If I'm tracking what a non-deterministic finite automata does in this situation, I say, well, okay, I start in this state, I take this edge on a 0, I take this edge on a 0, and I take this edge on a 0. And after that, in my next state, I've split into 3 branches. and I'm in 3 places at once. So I'm over here, and I'm where I started. So clearly, if we do this a lot, we're going to be generating branches of computation all over the place, and it might be a lot to keep track of. We'll talk about that in a minute. But certainly this rule is going to mean that we're keeping track of multiple branches at once as we consider the evaluation of our NFA. Rule number 2, sort of the opposite of rule number 1, no options on a symbol. This branch will die. So essentially, we'll remove that state from the set of states we're keeping track of. And add a little rule, if all branches are dead, we just reject. We have no more live computations. If all of our branches die before we finish reading symbols, then we'll consider the computation essentially aborted. So an example of this sort of thing, if I have a couple of states like that, and I read in, say, string 0, 1, what's going to happen? Well, I start in my first state. I read in a 0. I have a 0 edge and only one 0 edge. So I take it, walk over here, and then I read in a 1. When I read in a 1, I have no place to go. So this particular branch dies. And if it's the only branch of computation I had left, if it was the only one I was keeping track of, when I read in that 1, then my computation just rejects. So I forget about it, I stop tracking it. A third rule, sort of a special case of these rules. If you want to, you can see it as like a limiting case, but sometimes I think it's easier to think of it separately, is we're going to add a new special kind of edge called an epsilon arrow. So epsilon arrows indicate an extra free branch. So it's sort of like, the reason we call it an epsilon arrow, it's sort of like reading in the empty string. Instead of reading in a character, we're reading in nothing and acting on that nothing that we're reading in. This resolves after each computational step. So, for example, add an epsilon edge. And consider what would happen here on the input string 0, 1. So we'll track it through. Our 0 is very predictable, just like before. We take our 0 edge, we move to this state. And then, now before we do anything else, we notice we have an epsilon edge, and we resolve it before we take the next computational step. So we split off a second copy of ourselves, another branch. We take the epsilon edge and end up over here. But that's just another branch. This copy down here is still alive. And then when we read in the 1, we now evaluate it on our 2 copies, right? We evaluate it on every copy we have still alive. This copy follows this branch, and the lower copy follows the lower branch. So we're now tracking these 2 computational branches as they go throughout the machine. And then finally, rule number 4 is just a rule that tells us what to do if we have multiple living branches left over when we finish reading our string. This is a possibility we've introduced, so we should decide what we do when it happens. So we'll say we accept if any live branch of computation accepts at the end of the input string. So to add to the end example above, if this was a yes state, and this was a no state, this computation would accept because at least one live branch would have ended up in an accept state at the end of the computation. So we've got 4 rules, and we'll go through and do some examples so we kind of know what's going on a little bit more intuitively here. And this set of rules will allow us to expand the power of our state diagrams. Whenever we use one of these rules, our state diagram becomes the state diagram for an NFA, a non-deterministic finite automaton, because it uses non-determinism. Another way to think about this distinction is with these kinds of pictures. So we can think about a deterministic computation as just moving from state to state to state to state until we finish reading our input string, at which point we reject or we accept. A non-deterministic computation might move just from state to state, but it also might branch, right? It might move from a state to a set of 2 different states at the same time. From those states, it might move somewhere else. And then from those states, you know, a couple of these branches might die partway through the computation. And 1 or more branches might make it to the end, reading all the input letters, at which point some might reject and some might accept. And if just at least 1 branch accepts, then we are golden. This is an accepting computation. So hopefully that picture helps. Another metaphor that might be helpful for thinking about non-determinism, we've talked about splitting into multiple copies, branches. We've also talked about, well, you can think of this as making a non-deterministic guess. So you can kind of think of each split as the machine choosing to guess multiple different possibilities at the same time. And if either guess is correct, meaning it ends up in an accept state, then we accept the computation. So all we have to do, right, if we want to verify that the computation accepts, is find 1 accepting guess, 1 non-deterministic path through this tree of computation. And then a final metaphor that might be helpful is the idea of a separate process or thread when you're running a program. If you've ever written a program that creates a new thread and had to deal with multiple threads acting asynchronously, that's kind of like what's going on here. Sort of like we're tracking multiple threads at once as they make their way through our automaton. So let's see a couple of examples that hopefully will convince you that non-determinism is a useful thing to have when we're drawing state diagrams. So let's do an example on the alphabet 0. It's a 1-character alphabet, 1-symbol alphabet. That's totally fine. And we'll set our goal as recognizing the following language. The language of all strings W, such that the length of W, so remember this is our little notation for length or size. The length of W is divisible by 2 or by 3. Remember, when we write order like this, it's always inclusive OR. So if either one of these conditions hold, we want W to be in our language. So if we wanted to do this with a DFA without non-determinism, we might start by observing that we can make little gadgets that recognize 2 different pieces of this language. What I mean by that is, I'll call this gadget 1. And I claim this gadget recognizes all strings of zeros with length divisible by 2. Why? Because we're going to start at the left state, we'll recognize the empty string, and then we'll just keep hopping back and forth from state to state. If the string has 1 0, it'll be on the right, 2 zeros will be on the left, and so on and so forth. If we've ever read an even number of zeros and then stop reading an input, we find ourselves in the left. So this will recognize divisible by 2. And then similarly, we can create this little cyclical gadget. I'm saying the word gadget, which is a fun informal word, but it's also a word that we will use a lot. People talk about gadgets as like subparts of larger machines in theory all the time. And this little cyclical gadget will recognize strings whose length is divisible by 3 by the same logic as above. So great, we've got two little gadgets. These are both deterministic state diagrams. They don't use any of the rules we outlined above. They recognize, the first one recognizes the language of strings divisible by 2. The second one recognizes the language of strings divisible by 3. Now, you might observe that the language we're trying to recognize is just the union of these two languages. So you could go back and use our proof that the regular languages are closed under union, use the construction in that proof to create a complicated DFA on pairs of states that unifies these two diagrams, right? This would have, it would have 6 states, and it would be tracking both of these properties, divisibility by 2 and divisibility by 3 at the same time. So you could certainly do this with the DFA. But with an NFA, I claim that the task is much simpler. I can create a machine that recognizes either one of these two conditions by drawing 2 epsilon arrows from a new start state. And the reason this works is because whenever I read in a string, I'm going to start at the start state. The moment before I start my computation, I'm going to branch on my epsilon arrows. So I branch on this one, send one state over here, one branch over here, branch on the second epsilon arrow, send one branch down to the second gadget. And of course, there's technically a third branch, which just stays in the first state, but we can forget about it because there are no outgoing 0 or 1 edges, so it will die on the next step of computation. Now on the next step, right, what happens? Our first branch dies, and our second and third branches begin computing these two gadgets, these two languages, divisible by 2 and divisible by 3 at the same time. The machine accepts, remember, whenever any of our branches winds up in an accept state at the end of computation. So this gadget does in fact represent, this non-deterministic finite automata state diagram does accept precisely the language we wanted it to accept. Moreover, it's also probably a little bit conceptually and visually cleaner than the one we could have gotten by using our union construction proof to build a DFA to recognize this language. Let's do one more example. So example 2. This time let's consider the language sigma contains both 0 and 1. Scroll down a little bit so we're not paying so much attention to the previous diagram. And this time we'll set ourselves a different goal. The goal this time is to recognize the language of all strings W such that W has a 1 as the third to last symbol. All right. So if we think about how we as humans might recognize strings in this language, one nice thing we could do is count backwards from the end of the string and look at the third character. But our DFA, our NFA, neither of them have that option because they all read characters in order. So if we wanted to write a DFA that does this, we could maybe create some sort of working memory that remembers the last 3 characters in the form of a state. But an NFA can do something a little bit simpler than that. In particular, let's start just with the DFA that recognizes any string of length 3 that starts with a 1. Right? And hopefully it's clear why this DFA should work. We put in a string. I suppose if it's a DFA, we really should specify all of the edges. So on a 0, we go down to this essentially reject state where we stay forever. And if it's a 1, then we go to the right, move to the right again, move to the right again, and wind up in Q4. We always accept. There's a simpler way to write this DFA. But I like the way we've written it right now because it allows modification to become an NFA that recognizes our language above. The downside of this particular DFA is that it only works if our input string has exactly 3 symbols. It doesn't work for longer strings because it doesn't know when to start counting, when to make our journey to the right and start the process of trying to accept if we've read a 1, that's the third to last symbol. How we can fix that is by adding a couple more edges that make this non-deterministic. In particular, the reason this is an NFA is because I've duplicated the 1 edge. So now what's going to happen? I put a string in, and one branch, there's always going to be one branch that sticks around in the first state indefinitely. Every time I read in a character, whether it's a 0 or a 1, that branch will take the 0 or the 1 edge and stay in the first state. However, whenever I read a 1, I'll move across to state Q2. And then after reading 2 more characters, assuming the computation doesn't end, in which case the branches would reject, unless there's a branch in the end state, would get to Q4. So that's generally how this automaton is going to work. We're going to stick around in Q1, some branch is always going to be there, and then every time we read into 1, some other branch is going to shoot off to the right. If we have fewer symbols than 3 left in our string, I claim that branch is going to die before it gets to Q4. If we have more than 3 symbols left in our string, like we read in 1, 0, 0, 0, 0, 0, that branch will make it to the end, reach Q4, find that there are no outgoing edges, and also die. The only time this machine is going to accept is when a 1 is in the third to last spot, because in that case, we'll send a branch over to the right, we'll exhaust the last 2 symbols, and we will have a living branch in Q4 precisely when the machine ends its computation. So that's another handy use of an NFA. I also want to give you guys an example that precisely tracks the computation of an NFA. So you can skip over this part if you're very confident with tracking how an NFA works, but we're going to draw a machine that uses all 4 of our new rules, and we're going to track it in a little bit more excruciating detail with a lot of colors. So we'll go slow, we'll focus on piece by piece tracking multiple states and keeping up with the execution. So this is example 3 of an NFA. It's going to look kind of like our NFA above, but slightly different. So you may be able to tell by looking at this that this automaton will work slightly similar to the one we showed in example 2 above. Some state is always going to hang out in Q1, and then some branches are always going to hang out in Q1. Certain branches are then going to deviate off to the right. They'll survive this path if they contain a 1, 0, 1, moving Q1, Q2, Q3, Q4, or a 1, 1, in which case they move Q1 to Q2, take the Epsilon arrow, and then move another 1. And at that point, any branch of computation that makes it to Q4 will stay there. So this NFA state diagram, in fact, recognizes the set W containing all strings with 11 or 101 as substrings. But let's track the execution anyway, just so we can see how crazy it gets. For this, we're going to consider the string 101, and I'm going to draw all 3 characters in different colors, so we can kind of keep track of what's going on at any moment in time. This will help keep things just very slightly neater. Okay, so we start at our start state, and we read in a 1. The first thing we do is we branch, because we have 2 outgoing edges on a 1. So we go around here. We end up with 1 branch in Q1. We also cross this edge from Q1 to Q2 and end up with a branch in Q2. And I should remember, at the end of every round, we check for epsilon edges. So we also branch again and send 1 branch over to Q3. Now on round 2, we read in this 0. Our first branch is going to follow the 0 edge, and it's going to stay in this first state. There's no other 0 edges it can take, so it stops. Our second branch is in this second state. It's going to take the only edge it can take, which is a 0 edge. And finally, our third branch is going to start from the state Q3. It's going to find that it has no 0 edges, no outgoing edges from the state Q3, marked with the symbol 0, and it will die in this round. So after 2 inputs, we now have 2 surviving branches. Finally, we're going to read in our last one. So our first state, first branch, it's going to stay in state Q1. This same branch is also going to follow the edge, hang out in state Q2. This is going to branch again on the epsilon edge at the end of the computational step, end up at Q3. And finally, our branch in Q3 is going to take the only outgoing edge it could take, the 1 edge, and wind up in Q4. So at the end of our computation ends now, we actually have 4 living branches. We have a branch in every single state. I'll make a note here, if you're doing this on your own and you end up with 2 branches in the same state at the same time, you can just think about one of them because they'll act identically from this point on. But at this point, we do have the maximum number, 4 branches. They're all alive at the end, and one of them is in an accept state. So this is an accepting string, as it should be, because it contains 101 as a substring. So that's our more in-depth worked out example. A little note. If you're doing this by yourself, if you're on a legal pad, if you're reviewing these notes, one way to do this is by tracking live branches with your fingers. Which may sound silly, but I do it to help me evaluate NFAs. This is the recommended method in the textbook. And how you do it on this previous example is you would start with 1 finger on the Q1 state. You would then split into 2 fingers, tracking the 2 live branches, split into 3 fingers, tracking the 3 live branches at different points in time, and move your fingers around to follow where the computation is at any point. So if you do this for the example above, after the first step, you should have your fingers on the green dots. Second step, fingers on the blue dots. Third step, fingers on all 4 purple dots. So that's our sanity check. Now that we've done a few examples, I'll go ahead and give you the formal definition of an NFA. So we've defined new rules for our state diagram. We'll also have new rules for a 5-tuple. that formally represents this computation. And the idea here is that it'll be very similar to our DFA, except instead of mapping from state to state, because we're no longer deterministic, our transition function will map from each state and symbol input to a set of states, right? To everywhere you go to after evaluating one symbol. To talk about sets of states, do one quick notational definition that'll help us address this. I want to make sure you know what a power set is. The power set of set Q, denoted curly P or fancy P of Q, is the set of all subsets of Q. So just for an example, if we had the set Q equals A, B, C, then the power set of Q is the set of all subsets of Q. So the null set, the empty set, is always a subset of Q. The set containing A, B, and C, all of those are subsets of Q. We've also got AB, BC, AC, and finally ABC. So the size of the power set is always going to be 2 to the power Q. And that's just because if you want to count up all possible subsets, one way you can do that is by realizing you've essentially got Q binary choices, whether or not to include each element of Q in the subset you're making. So you've got, Q yes or no decisions. The number of subsets you're going to have is 2 times 2 times 2 times 2 Q times. So this should be 2 to the 3 or 8 in size. 8 subsets. So now we've got just a notation to talk about all the subsets of Q, which will let us write our definition of an NFA. So a non-deterministic finite automaton, also known as an NFA, is a 5-tuple Q sigma delta Q0 F, just like for a DFA, where Q is a finite set of states, sigma is a finite alphabet. We'll come back to delta in just a second because it's going to be the only tricky part. Q0 is the start state. F is a subset of Q, and it's the set of accept states. And then finally, the transition function delta maps from Q and sigma sub E, which we write as shorthand for the union of the alphabet and our little bonus symbol, the empty string, because now we're allowed to take edges on empty strings. So this will tell us, give me a state and give me an alphabet symbol or epsilon, and it will map to the power set of Q. And that's our transition function. And this is exactly what our NFA is doing, right? You look at a state, you give me a symbol, or you give me the empty string, and I will tell you a set of states that we're going to end up with branches in next. That set of states is, by definition, a subset of PQ, or a member of PQ. We say that an NFA accepts a string W equals W1, W2, W3, dot, 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 WM, where all of these WIs are in the alphabet sigma plus the epsilon string. If there exists, and now what we want to do is write down an expression for an accepting computational path, right? Some branch that ends up in an accept state after reading in all of these symbols. So if there exists a sequence of states R0, R1, R2, all the way to Rm, such that, well, our accepting branch should start at the start state. That is, R0 should be Q0. Each next state that we get to should be a legal path from the previous state. And note that I'm writing the include sign there because delta of Ri, Wi plus 1 is actually defining a set. So all I have to do is make sure that my next state is in the set of states that I send some branch to from Ri. And this is for all the relevant I. And of course, Rm should be in the set of accept states. That's our full formal definition of an NFA. It's these 5 states. Again, the only thing that differs from the DFA is the fact that we're mapping to power sets and the fact that we're mapping from an input alphabet that includes epsilon. And then we accept whenever we can identify a sequence of states with legal transitions between them that end up at the accept state. The last thing I want to do before we end this part is write down an NFA state diagram and show you how to extract the formal definition from it, just to make this concrete. So again, if you're rock solid on this, you can skip to the next video. So here's our example. And this is writing the formal definition of an NFA state diagram. So we'll write down an NFA state diagram that we've seen before. This will be our one that recognizes all strings with a 1 as the third to last digit. Actually, no, let's add this epsilon edge because if we do that, then we'll get to see what epsilon looks like when it's a part of our transition function. So we'll make this slightly different. And most parts of the formal definition corresponding to this NFA are going to look pretty familiar. So this corresponds to an NFA N equals Q sigma delta Q0 F with Q equals all the states, sigma equals our input alphabet, 0, 1. Q0 is just our start state, Q1. F is the set of all accept states, so just the set containing Q4. And then finally, delta will be a transition function. Remember, our transition function will map from the set of all input symbols plus epsilon and any one state to the set of states we end up at next. So if we look at Q1 here, on a 0, there's one outgoing edge that takes us back to Q1. On a 1, there's two outgoing edges that take us to Q1 again, and also to Q2. So this is a subset of all the states, Q1, Q2, and it's also a member of the power set of Q. So it's in the output of our transition function. There's no outgoing epsilon edges. So on epsilon, we go nowhere. We go to the empty set of states. From Q2, on a 0, we go to Q3. On a 1, the branch dies. On an epsilon, we also go to Q3. From Q3, on a 0, we die. On a 1, we go to Q4. And on an epsilon, there's no epsilon edges, so we die. And then finally from Q4, we stay in Q4 on a 0 and on a 1, and there are no epsilon edges. So that completes the formal definition of the NFA corresponding to this NFA state diagram. So that's all for this part. In the next part, we will show you how to convert any NFA to a DFA. So thereby showing that with DFAs, we can technically recognize all the same languages we can with NFAs. Thanks for watching.